Hello everyone. In this video clip today, I'm going to start chapter 4 with the two first sections, 4.1 and 4.2 in chapter 4. Those basically, the first one, 4.1, actually a review, a recall from your college algebra. We talk about the maximum and minimum values. So basically, we have two types of max and mean, the absolute max mean and the local max and mean value. So let's recall it first before we move on to section 4.2, which is something new called the mean value theorem. So we're going to start with the max and mean value. Hang on a second. Okay. So let me show you a graph, okay? Let's say I have a graph. Okay, it's like right here. It ends right there. The graph starts right here, go up, and then hit some top, and then go down, hit the bottom, and go back up. So for absolute max means what? The highest point on the entire graph. Entire graph means we're talking about the entire domain for the function. So for absolute maximum, it's a point in this particular graph is going to be right here, the highest point for the entire graph. So let me change it. What if I have the graph, oops, stop right here. Now what? This point will be the absolute maximum because it turns out that what this time, the second graph right here, this will be the highest point. Absolute maximum is the highest point. So if you say what? X equal to C is the absolute maximum, it means what? F of C is greater than or equal to f of x for all x in the domain. And you know what we mean by in the domain? On the entire function, you find a point. This is the point C right here. This is C. Okay? This is the highest point on the domain. So for the previous graph, if it goes all the way up here, then this is going to be the point C. And I never say that you're going to have a unique absolute maximum. You may have a lot of maximum if you can find multiple points that got the same height as the highest, say the sine function you guys see. Okay. It's got a lot of absolute maximum. As long as this is the highest point on the entire domain. It's in the entire domain. You find the point C. So that's bigger than any other point. F of C is higher than any other f of x. Okay? And similarly, if you want to define absolute minimum, all you have to change is the word max into the word min, and greater than that become less than or equal to, it means what? The lowest point in the entire domain. You got the absolute minimum. Okay? Now, let me talk about local max and local min. I'm going to give you a little bit more precise definition compared to the book, because better definition going to give you better understanding. Of course, there's nothing wrong with the book. It just give you better intuitively definition. Later on, they're going to give you a precise definition anyway. So let's talk about local max and local min. Let's go back to our graph. Okay? So we're not looking at the entire domain anymore for the absolute. Now local means what? We only look for an interval. Okay? So small interval. And if within that small interval, you can find the highest one on that small interval, that's called the local max. And similarly, if you can find another interval, small interval, such that we have a lowest point within that interval, then we call it the local minimum. And of course, the local max may not be the absolute maximum, may not be the highest point for the entire graph, but locally, this is the highest point. Same idea in here, the local minimum may not be the absolute minimum. Alright? And vice versa. So, you want to find the local max, you have to look for the interval. You have to start with the open interval. That's just what it is, open interval, okay? And you find the highest point on the open interval. To find the local minimum, you look for the open interval, you can find the lowest point on that open interval. Why I say that the local max may not be the absolute max, and vice versa. See, this is a local max, right? Not the absolute max. Are we good? And the absolute max may not be the local, because we have to stick with definition. In order to find the local max, you have to find the open interval. All right, and we use our regular topology in here that this endpoint right here is actually an absolute max, but we cannot find any open interval. That's the high point. You only have open on one side, closed on the other side. Okay, so this, by definition, this is the absolute max, but it's not really a local max, because you don't have an open interval around that point. This is the end point. Okay? Unless you define, using topology, you define a half open at the end point is still open set, but that's for a later story. For now, real number, this is not open interval. Okay, so let's give you a more precise definition. X equal to C is a local max, maximum if f of C is greater than or equal to f of x on an open interval. An open interval. Interval I. Okay? I stands for interval. Where C is in I. So what I'm trying to tell you is this. This is the I that we're talking about right here. This is the open interval I. I is interval from here to here. It's going to be open interval, all right? And within that interval, f of C is bigger than any f of x when C and all the x's in this interval. All right? And of course, you have definition of absolute max. You can just simply change the word max to word minimum, and greater than that becomes less than or equal to, and you have the definition for minimum. Same idea. And now we're talking about this interval right here, from here to here. This is my new I, open interval. And local minimum of what? F of C is smaller than any other f of x within that interval, where C is, of course, going to be in that interval. C is right there. Okay? And this is the almost the end of 4.1, I think. Let me double check before we move on. Okay, let's use the same graph right here. Why do we need to learn about local max and local mean? Max and mean in general. What does it use in calculus? How does it apply to calculus? Now, what if you have a smooth function, a differentiable function, a function that you can take derivative? You guys see that at the point, say local max right here, we talk about local max and local mean, okay? If you have a local max right here, what happened? The tangent line on the left-hand side is going up, slope is positive. The tangent line for the graph on the right-hand side of the local max is negative, going down, right? See? And you see the change of the slope of the tangent line. And remember what I mean by the slope of the tangent line. This the derivative of the function. Right on the local max, we have a horizontal tangent line. In other words, that point right here, C, f prime of C is equal to 0. You know that the derivative of the function is no more than the slope of the tangent line. And same thing here, this point right here, let's go D then. And, f prime of D is here is also equal to 0. Okay, so this is the preparation for you guys to learn in the following sections. I think it's 4.3. It's about how to find a local max and local mean. You see the hint right there? If you have a continuous function, right, it gotta be continuous. Or more than that, it's gotta be differentiable. Continuous and then differentiable means what? You can take the derivative of that point. You see, we're talking about the derivative. And if you can have a local max and local mean, then for sure the derivative of that point will be equal to 0, because graphically show you what? Graph going up, it hit the top, go down, and the slope positive, change to negative, is continuous and it's smooth, means what? Differentiable. Then at that maximum right there, the derivative is going to be equal to 0. But that is for later. For now, at 4.1, all I need you to know is the idea of local max and local mean. Okay, now let me talk about the mean value theorem. 4.2, mean value theorems, abbreviated by MVT, mean value theorem. In short, you see that three letters MVT, understand it in math, it's mean value theorem. So you have a function, okay, it's closed interval, so start somewhere right here, end somewhere right there. Let me put it at the XY, x-axis right here, the y-axis right here, okay? So this is A, this is FA. Let me just extend this a little bit more. This is the y-axis. This is B. This is FB. If you have a function on a closed interval from A to B, you see that we have two endpoints, A is solid dot, and that B is still not a solid dot. So we have a closed interval from A to B. Okay? And the function, of course, is going to be continuous and differentiable, so smooth function. All right? You can take the derivative anywhere on the curve from A to B. Okay? And for that is differentiable. Differentiable means that you can take the derivative. Differentiable on AB. Okay? So this is the setup for the theorem. Say what? You have a piece of curve that is smooth, right? Continuous, and take the derivative anyway. And if you take 2 points A, FA, and B, FB, you connect the 2 points, you guys see what you got? You have a line. Can you calculate the slope of that line if you know 2 points? Slope of a line is what? Change of y over change of x. That's another word. It's going to be FB minus F of A over B minus A, right? FB minus F of A over B minus A, change of y over change of x, is going to be the slope of that secant line, the green line that goes through the 2 points A and B. Okay. Now let's get to the theorem. The theorem says this: if the function is continuous and take derivative, is be able to take derivative, then for sure you can always find a tangent line somewhere between the point A and point B, such that the tangent line is parallel to that secant line. And this is what I'm talking about. You can always find a tangent line to curve. Okay? And can always find one. It doesn't mean that you're going to have exactly one all the time. You may have more than one. In this particular example, you may have another one right here. See? You can always find a tangent line that is parallel to the secant line. Okay? So how do you indicate the line of parallel? The two lines are parallel if they have the same slope. This is the slope of the secant line. What about the slope of the tangent line right here? The theorem said it. You can always find a point C between A and B, such that f prime of C is equal to that quantity right here. Okay. All right. So let me move it down a little so I have some more room to write. Differentiable on AB. Then there exists a number C, A less than B, I'm sorry, A less than C, less than B. What we're trying to say right here, number C is between A and B, such that FB minus FA over B minus A is equal to f prime of C. Okay? And this is all about the mean value theorem. And you guys see the idea already. Let me just repeat it one more time. You have a closed interval from A and B, right? Why do we need the closed interval? Because we need the endpoint to find the slope of the secant line. So we got point A, we have f of A, we have the first point. We got the point B right here, f of B, we have the second point. And we find the slope of that secant line by what? Changing the y, so fb minus fa over b minus a. You have it right here. And the function is continuous and it's differentiable, so the function is smooth. And The theorem says what? You can always find at least one value C somewhere between A and B. There exists number C, and C is between A and B. All right, such that what? The slope of the tangent line through C. And how do you find the slope of the tangent line? You take the derivative at that point, right? It's gonna be the same as the slope of the secant line. In other words, the tangent line will be parallel to the secant line. And you may have one, may have two, may have three, or maybe more than that, but at least one. And this is the main idea for the mean value theorem. And you guys got the idea of it. And let me see if I missed anything in here. Pretty much that's it. Okay, for the mean value theorem. Let me come back and talk about max and mean in here. You guys see in this graph right here, for sure it's going to have an absolute maximum. Where is it? Right there. Okay, you have a local maximum right there. Okay, local minimum right there, and this is absolute minimum. And just for this example, but in general, if you have a closed interval and a function continuous on a closed interval, closed interval means what? Let's stop right here. Then. The starting point and the end point is a solid dot. Okay, then I claim that you will always, for sure, have a local max or local mean. I'm sorry, absolute max, absolute mean for sure. May not be local, but for sure absolute. At the line right here. Right. You have the absolute mean right here. You have the absolute max right here. And it's never changed direction, never been decreasing, so you don't have a local max or local mean, but always have absolute. Okay. The second example right here, this point is the local maximum because I can find the interval around that point, so the highest point. It is also the absolute max because for the entire domain from A to B, this is the highest point. So this point is just the end point. This point is the absolute minimum, but it's not the local one because the local one is right here. You cannot find the open interval around the point. Instead, this is the lowest point. It's only have open on one side. It's closed on the other side. That's why it's the absolute minimum. Okay. What if you have a graph like this? This point right here is the local maximum because I can find the open interval. It is also the absolute maximum because it's the highest point for the entire graph. Similarly, this is the local minimum. It is also the absolute minimum. Okay. So for sure, if a graph is continuous on a closed interval, you will have the absolute max, absolute mean, but you may not have local max or local mean. Like this example right here. And I think I should stop right here because I need to save something for the next section. The next question is for you to think of how to find the local max or local mean, or how to find the absolute max and absolute mean. Okay, that's for the next section. So let me stop right here. Thank you for watching, guys. If you have any question, please ask. Have a good day.